Okay. Hi, everyone. Thank you for being here today. My name is Nicolas Schneider. I work at the EDHEC Climate Institute with Ricardo Reboneto. And today I'm going to show you a seminar on climate information, granularity, and projections of physical risk impact on economic outputs. So basically in today's presentation, the slides don't change. 1 second, sorry. Okay, so basically in today's presentation, the outline of the session will be to show you that climate impacts sectors and space heterogeneously, and therefore global average indicators are less reliable for investors. Then we're gonna show you the latest development in terms of data developments, notably given by NASA and other mega providers, and what does it tell us about the transformation of our sectors. Finally, we're gonna tackle the burning topic of the day, granularity. What does it mean? How does it help us for physical risk assessments and our future ability to adapt to climate shocks? Finally, we're gonna show you a case study using the Mediterranean basin, and we're gonna show you how to project climate shift impact on economic outputs and how to distribute resulting simulation over time and space. We're gonna deal with uncertainty. We're gonna show you how we try to account for it. And finally, try to summarize up for you guys, what are the main implications for investors in search of regional principles. So climate change impacts space heterogeneously. So in front of you is a spatial distribution of global surface average temperature anomalies recorded last year. And as you can see, although we have reached recently 1.5 degree temperature average increase compared to pre-industrial period, this is only an average. And as you can see on the map, you have hotspots, which means that some places are experiencing higher temperature shock than others. And so the point of saying that is telling you, if we're relying on a global surface average metric, it is hiding some key information that we need. The second point is sectors. Climate change impacts sectors heterogeneously as well. I'm giving you an example with the two main weather sensitive sectors we have in our economy, agriculture and energy. On the left-hand side, you can see this is basically how we see climate change impact on land productivity. On the bottom, you have the temperature distribution. On the left-hand side, you see log yield responses, which are basically a measure of land productivity. And as you can see, beyond a certain temperature exposure, we have estimated empirically nonlinear temperature impacts, which means that as temperature is rising, you have cumulative increasing marginal damages to your land productivity. Now, on the right-hand side, you have energy demand. So we're moving from supply of crop to demand of energy. Energy demand is rather a U-shaped relationship. What does it mean? Energy consumption is an adaptation strategy to outdoor temperature exposure. As you move towards extremes, whether hot or cold, you are consuming energy, whether gas or electricity, to heat or to cool in the winter or the summer. And that is why we observe a U-shaped relationship. Now you're telling me, why do we care? Well, it cares because these two main sectors are part of the global GDP, and they matter a lot when it comes to forecasting future damages of climate change. So basically, 2024 is a kind of special year because we have reached 1.5 degree average surface temperature increase compared to the pre-industrial period. When I'm showing you this beautiful graphic, something is missing. What does it tell us about the intra-region heterogeneity stories? And it is the same for output. This is a result from a very famous study that is called Burke et al. And they've been able to draw very, very famous damage functions, which are basically estimates of future economic losses as temperature is going to rise. But as I'm showing you this, something is missing, which is the sector, industry, and asset class specific risk exposure. And we know that investors, decision makers, are increasingly interested in regional information. So I'm showing you a very simple example of why it does matter to us. The US Securities and Exchange Commission, which we're going to call the US SEC, has implemented in March 2024 the climate disclosure rules, which basically ask publicly traded companies to display activities of mitigation and adaptation to climate risks. Well, something else is missing here. If you are trying to display your future adaptation strategies, those must be determined by your forecast of adaptation costs. To know your adaptation cost, you need to know your risk exposure. To know your risk exposure, you need to rely on some granular data if it is available. And so this is where the big data provider find their contributions. So in front of you is literally a screenshot from one of NASA's Center for Climate Simulation website. And these people, very smart people, have been able to process, store, and make freely accessible on cloud repository big climate data sets, which I'm going to call the Alexandria Library. And these data sets are big ensembles of very highly timed, spatially resolved information, whether historical measurements or future simulations, and are therefore incredibly heavy. They are very heavy. They have specific file structure, which we would call NCDF files or rasters, and therefore should be processed and handled using what we call high-performance computing systems, HPC. High-performance computing systems, in one word, using Wi-Fi and coffee at Starbucks. You can access online to a supercomputer located in California, extract data, process it, collapse it, export it. And this is what is changing the game for us today. So those are kind of screenshots that I took for you of what it looks like. So on the top right is basically a window to access a cluster. A cluster is once again a supercomputer you can access remotely. This is a Linux language. You can select the number of gigabytes you want. And on the left-hand side is an example of our studio workflow we will use to process these files. On the bottom left is Google Earth Engine, which is another mega provider. And on the bottom right is an example of Microsoft Planetary Computers, which in French is Ordinateur Planétaire. All of these things, you can access them remotely. They are providing you data, and you should do it, you should use it, because you can. And so what does it mean to us? Well, for a long time, our approach to climate change was very much temporal. What does it mean is that you've probably seen figures, a global figure of a target over a very long-term window, and I often take the Paris Agreement, for instance, 1.5 degree target by 2050. And this is also by communication convention that many people have also done that with some macroeconomic insights because it's easier and it allows us to summarize to the reader key information. The issue is as follows. We know that in the future, the frequency and intensity of climate shocks will increase. The spatial distribution of these shocks will be increasingly heterogeneous. Let's take an example that was very recent. 2025 January, we had in Los Angeles catastrophic wildfires. 2,000 miles east in Texas, we had a catastrophic snowstorm, both of them causing increasing damages to infrastructure, people, and by implication, assets. So the question is, should we use this data to project and locationally distribute future physical risk impacts on given outputs of interest to investors? My answer is yes, because we can. And so granularity really means approaching climate shocks in a spatial fashion. You give increasing attention to shorter term windows, and you can finally have some accurate measures also of extreme weather events. So we've prepared a case study for you. Say that we have some industry that is interested in climate-related damages on the most aggregated economic output, GDP. And they have asked us to elaborate and deliver a product answering this question and focused on this area. We could follow and propose a stepwise approach, which will be composed of 4 steps. The first one, large-scale processing of historical, economic, and climate information. Second one, we will use this data, build an estimation data set, run econometric calibration, and estimate response functions using the data set we've built in step 1. Step 3, we can project future climate change impacts on outcomes using the equation we have empirically calibrated in step 2. Final step, you can decompose and distribute your simulated impacts obtained in step 3 over multiple vectors, which include times, space, RCP climate change scenario, global climate model, etc., etc., etc. So I'm giving you kind of an example here of the granularity at which we will work together if we were to conduct this case study. So in front of you is basically a map of the global administrative area, so provinces, equivalent of regions for France, say Rhône-Alpes-Auvergne. And you have 16 to 2,000 of them in globally distributed. And as you can see, if we subset the Mediterranean basin and you look at this map, you can see that we start to have quite an interesting granularity we can work with. If we wanted to dive deeper, we could basically work at the county level, which then moves us from 166 countries globally to 2,000 provinces globally to 45,000 counties globally. So as we move further into the resolution, it becomes increasingly interesting because basically you can get very tailored and fine-scaled projections of climate change impacts. So first step, so we will use high-performance computing system, and we can handle, sorry, just gonna drink some water. We can handle the processing of historical climate information, which basically means that we can use our cluster, access remotely to some NASA providers' websites, and process temperature and precipitation data at the 0.25-degree resolution, and we can have that all together ready for our estimation data sets. I wanted to show you this map that I've built for you. So basically, this map is a measure of the linear trend in average temperature in each of the 200, almost 50,000 unique grid cells for which we have daily time series of information data. And as I'm trying to show you here, is that a trend of 1, which we observe here in some areas, mean that the temperature at the end of the period were 1 standard deviation higher than at the beginning of the period. And here, right before your eyes, without any climate simulation, any climate forecast, we have been able to show you climate change. This is historical measurements, and you are observing a shift in temperature, and you're also observing that it is spatially distributed in a heterogeneous manner. And so now that we have this big data set that we have processed, the question is, we're gonna need to spatially aggregate it. We're gonna need to temporarily collapse it so that it's matching the spatial and time frequency of our output of interest, which is GDP, at the provincial level. And so to do this kind of big collapsing and aggregation process, there is a whole use of weighting methods, basically to account for the heterogeneous spatial distribution of output and population intra-country. But just know that we used GDP values that are reported at the provincial level from something that is called the dose data sets, and that allow us to basically have year-to-year time series of GDP information for each of the provinces in the Mediterranean basin. Now, you will tell me if you wanted something more, something with a higher resolution, there is a way to use what we call spatially downscaled economic products. Some very smart people have been able to use satellite from space and observe at nighttime the lights over the Mediterranean basin. And using this light distribution, they've been able to spatially downscale national time series of GDP across regions up to the kilometer square. And doing that, it allows you to really start having a heterogeneity story about the distribution of economic production, which is often communicated as a national output. But now you have this distribution at a more granular level. So basically, once we have our estimation data sets, we are linking year-to-year historical records of regional product per capita to plausibly exogenous variability in climate exposure. We're going to stick to temperature and precipitation, but there is a whole lot of climate components we could include in it. And we're going to stick to the most obvious variables, so average and some components of extreme weather events. We use an econometric artillery, and I only need to tell you that we control for many factors in order to draw something we call a response function, which is basically our understanding of the general global relationship between temperature and GDP. And we get a nonlinear effect. There is a very famous study from Burke and al. That came out in a Nature paper, which was groundbreaking for most of the field and many businesses. And they have found a relationship which is drawn in blue here. And at EDHEC, using different climate data and different resolution of data, we've been able to match the best guys in the world, which gives us a little bit more confidence as we are holding the lights in the darkness of research. So then, once we have this response function, we're going to try to compute and to test for robustness check. While we're doing that, we're getting a figure, we're getting a nonlinear relationship. We want to make sure this is something we can generalize and it's not the result of a composite effect. Here on this slide, the only thing you need to know is that we try to check for the fact that the nonlinear response we observe is not due to hot countries being poorer on average. And we test two different models, one that accounts for some GDP baselines, one that doesn't, and we find the same results. In a nutshell, global nonlinearity that we found before is driven by differences in countries' average temperature and not GDP. Now that we have estimated a robust econometric model, we can run the projections. So to run the projection, we're going to project future climate shift-driven changes in output per capita by forcing an ensemble of climate simulations into our regional GDP model, which we have just calibrated using historical data. And so how do we do that? Well, we need data. We need a lot of data. So we're going to process and extract high-resolution simulation of climate change. And basically, we're going to use a NASA's Earth Exchange Globally Daily Downscale projection that I'm going to call next GDP CMEP6, which we're going to subset over the Mediterranean area. So basically, these big data sets is an ensemble of 30 global climate model simulations that have been downscaled in times by day, over in space by 0.25 degree resolution, which enable really us to work with a very big matrix of data, which we combine with our high performance computing system and enable us by year of data to have 4.5 billion rows of information that we can then compute, collapse, and run our projections with. Once again, because these data sets are huge, we work on the cloud computing system, which enable us to ensure that we have enough storage and economies of scale. So here is a picture really of what a supercomputer looks like. A supercomputer is located in this kind of like big warehouse. They have their own cooling system, and they allow you really to run big computation tasks. And on that case, for instance, for next GDDP CMAP6, I'm showing you a snapshot at high resolutions of the simulation we have of climate change over a certain component, say temperature, in a given future, according to a certain scenario of climate change. And so something interesting here is that we have to run something that we call a decomposition exercise, which means that for each province of the Mediterranean basin here, we have an ensemble of more than 2,000 unique simulations of climate change impacts on our output of interest. Why do we have 2,000 unique simulations? Because we have many climate components. We have many forms of functions about the intensity of the effect. We have some scenario where we account for persistence versus not. And we have our set of global climate model, EDHEC, et cetera, et cetera. So think about this map as something that will be on a website where you can click on it and get 2,000 unique simulations of future impacts. This leads me to the next topic, which is going to be uncertainty. If you trust all of these simulations, good. We take the multimodal median and you have one number of interest. If you don't trust them, we can subset, account for further uncertainty until we can narrow down a result that fits with our approach to this topic. And so something that is interesting in that case is, as you can see here, so this is how is organized our results. So here you have our provinces. Here you have our global climate models, our SSPs here, our EDHEC, and the different simulations we get based on the different model we choose. And so we have a lot of temporal and spatial and model granularities. As I said, more than 2,000 unique simulations per province, which allow you basically to feature uncertainty in your products. How do we do that? So here we have different functions of damages that we have drawn over time according to certain scenario. And the solid line is basically the multimodal median. But as you can see in the shaded area, we get what we will call the distribution of likely global climate models. What does it mean? Well, we know that some of the simulations we have are not certain, and so we try to account for a bigger bracket of our impacts. And to do that, we choose 15 likely models. How do we do that? So basically, we know that the estimate of the macroeconomic effect of climate change are model sensitive. And we also know that the last generation of simulation of climate change are, for some of them, too hot. And so we select a subsample of 15 likely global climate models that forms the basis of our projection exercise. So we went from 30 to 15, and from these 15, we compute the multimodal median to narrow down our results to a few final numbers. So now as a conclusion, if we recall the case study, we have an industry that is interested in having damages, estimates of climate shocks on output in the Mediterranean regions, and they want to have a story of the intra-country heterogeneity. We can, right now, today, elaborate a big panel data set and estimate the regional, gross regional product per capita responses to temperature and precipitation, and have something that is calibrated and that covers 95% of global economic production in the Mediterranean basin. We can then project climate change-driven impacts on gross regional product by forcing our ensemble of CMEPSIS global climate model simulations into our regional GDP model, which we have calibrated prior using real historical data. We have our subset of 15 likely global climate models. We are able to distribute our results over time, over space, but also over warming scenarios, moderate, aggressive, vigorous, and that really allows us to draw heterogeneity stories intra-country. We can then, if country average, we can force some of these estimated shocks to output into a computable general equilibrium model, which basically will help us to quantify other macro scale implications after adjusting for some external parameters. Moving forward, you will probably ask me, who cares and why does it matter? Well, you must know that the estimates of global economic damages from climate change, they have granular origins. And we are able to see them, to explore them, to exploit them, because we have the right infrastructure. If the things have granular origins, that means there is some inequality stories to draw. There was a recent article from Natixis Flash Economics Communication that was saying that investment to avoid global warming is the most profitable of all investments. At EDHEC, we also say that there is a near certain likelihood of incoming extreme events that are getting more frequent and more intense over time, while investing in mitigation allows you to avoid an end-century catastrophic scenario. There is a near certain likelihood that at mid-century, the frequency and intensity of future shocks will increase, and therefore, something that is crucial is also increasing our adaptation capacity. Our work aims at increasing our understanding around adaptation, and we try to answer 3 key questions for investors in search of regional information. What is the size of future shocks locally? And how do they distribute spatially? How do they scale up globally? How much will it cost? Who's going to pay for it? And there is some real-world application to it, as we can talk, for instance, about the real estate industry. So I'm going to just take an example of the US recently because of the recent media coverage given by the wildfires in Los Angeles. In the US currently, we have 2.6 million homes that are rated at a moderate or severe wildfire risk alone. That means that some insurers right now in California are leaving the state and are stopping to cover some homes. It implies that for a lot of these locations, people will pay enormous climate premiums to be able to obtain insurance, and in some cases, won't be insured anymore. The contribution together of high-performance computing systems, large-scale processing of climate information, high-performing estimation models allow you to answer the following question for investors. Where, when, how severe, how much? And this is where we find our contribution. So at a conclusion, this not is only a case study of a brief example of what a feasible application could look like, but there is way more that is feasible also, focusing on some sectors or specific assets, and they can be deployed. Thank you very much for your attention, and I am ready to answer any of your questions. Thank you. If there is no question, yeah.
The last slide about the wildfires in the US. What other impacts would you say are expected besides the real estate price? Can something else be justified by the economic models that are forecasting what can wildfires cause in the future in terms of economic issues?
Wildfire alone?
Yeah, wildfires specifically.
So, well, so real estate is a quick case study because it impacts pretty much all of us. But something that is very interesting in that case is even land productivity. Like wildfire is affecting major infrastructure. It's putting at risk roads, bridges, power plants, cropland fields. And so basically what is going on is as temperature is rising combined with high wind speed and very low specific humidity, you get a higher wildfire risk in some area that costs a lot of money. For instance, Los Angeles, the estimated cost for now is $150 billion. This is huge. Who's going to pay for it? Insurances? A lot of them will go bankrupt. So right now, there's going to be a sort of sorting effect in society where very few people will be able to afford a wildfire insurance for their homes, while others will move. And so with wildfire risks, there is connected to it the question of intra-country migration. People are moving. They're moving up north. In the US only, we have seen enormous migration going from Florida, Texas, California, all the way up north. Because we know from the simulations that up north is going to be cooler. And so this has major implication for land prices, housing prices, and all of this. Did I answer your question?
Is there any solutions to fight using fires?
Well, I am not explicitly a specialist on wildfires, but there is a lot of people that are working at, so basically reducing the number of things that can fuel the wildfire, particularly vegetation. That's why there is some work right now of some people that are trying to couple temperature measurements, wind speed, wind direction, remotely sensed measure of vegetation to be able to forecast wildfire risks. But beyond wildfires, think about the Milton hurricane last year in North Carolina. Massive. It wasn't wildfires, it was something else, massive flooding. And so what is going on right now, basically, is that we are observing in the current period, rising frequency and intensity of these extreme events. Our argument right now is to say investment in mitigation is crucial, but in parallel, you should increase cities and industries' adaptation capacity. Okay? Any other question? Yes.
So how accurate are the analysis? Imagine, let's say I have like a house in California, San Francisco. How accurately can I use this platform to know how much my house is at risk to be subject to the wildfires? Like, can I know exactly?
Oh, there is actually major companies, startups that call themselves scale-up today that are working on this topic. So basically what major startups in London and even the United States have done recently is they've been processing this data. They have layers of information and they have matched it with measures of building footprint, which is geospatial data on buildings, and have been able to compute a wide range of risks, exposure, current and future of these houses. So let's do a very simple one. You have a house in Miami. It's a high risk, very expensive area. You know that at some point, the simulations we have of sea level rise, average sea level rise, will make your house flooded. And so there is some increasing work right now of some people that are trying to identify what is the shortest distance to the low price, low risk area compared to the high price, high risk area of Miami. And technically, this is where we think the real estate developers are going to move to. And so you can do that using basic computing systems. The idea is pretty simple, which is if your house is flooded and you're a massive real estate developer, where do you invest next? This is just capital movement, you know. Any other question? Yeah.
In the previous slides, you get something about the incorporating different temperature forecasts and just global weather patterns into one.
Yes, yes.
And I was going to ask, do you use the biggest weather platforms like the GFS and the ECMWF?
Exactly, yeah.
You don't.
So yeah, no, ECMWF basically is a European big organization that created something that is called ERA5, ELI5, which is a massive 0.25 degree resolution data set. And that's very interesting, particularly for historical information. There's a lot of people that use that because it has a global coverage. Now, this is only today, I showed you an example of a case study that we need to deliver, say, and we have to find a solution. We are swimming in data right now. So there is new mega providers that are entering the game and the competition. And so our industry is growingly changing. There is this spatial momentum, and many companies, many agencies, and even governments are increasingly relying on spatial information because now we can. And so you can give a very tailored, precise story to this homeowner in California because you now have the data to do that. A few years ago, even 10 years ago, we could not do that. But we have now big players like Google Earth Engine, Microsoft Planetary Computer. All of these big players enabled you with Wi-Fi and coffee to access remotely to Super Engine and process this data. And now there is even smarter people that are working at downscaling this data. Downscaling means that they're able to distribute measures that they have of the data at a higher spatial resolution. And actually, a few months ago in the United States, some people have been able to downscale global climate simulations at the kilometer square level. What does it mean? For each kilometer square in the United States, you have a massive daily time series of global climate simulation by weather components, temperature, precipitation, etc., up to 2,100 by SSP, RCP scenario, climate change scenario. So it really allows you to draw multiple possible potential trajectories of climate shift and fill out the bridge by saying, what is the size of the shift? What is the implication of the climate shift impact? So you see at two different stages in this supply chain. Understanding the local shift in weather components, understanding the climate shift effects on output of interest, GDP, energy demand, land productivity, real estate, physical assets, power plants, etc., etc. The most important thing to remember is climate change is a public good problem that treats everything. There is no control group. There is no place not affected by climate change. But we know the magnitude of the effect will be extremely heterogeneously distributed. And so my old mentor in the United States used to tell me, assume that God is not with us. And it was a good way to tell us that research on this topic is really hard, but we can provide some answers because now we have some data and methodological constraints that have disappeared. And so we should do it because we can. Okay? Well, I can check online, but I think we could. Yeah, I think we are good. No question online? Oh, yeah.
If I understood well, at some point in the case, you said that in the Mediterranean basin, you said that the variation of temperature is not really correlated to the GDP. So poor countries are not the reason why the variation is higher.
Mm-hmm.
So, like, why is it? What is it correlated to? And is it the case everywhere in the world?
So the point of doing this form of estimation, let me go back to that slide for you. So Okay, so basically an econometric model, without entering the details today, we are trying to understand what is the relationship between temperature and output. More importantly, if there is one standard deviation increase in average temperature exposure, what is the response of output? Once I control for time, other form of indicators, institutions, etc., etc. The point of doing that is because it increases our understanding of what is this relationship that we're gonna call a transfer function. And so when we do our projections, we have the calibration of this relationship. We have something that we call semi-elasticities that are only the parameters we've estimated. And we use that and we combine that with our delta. The delta is delta temperature, delta precipitation, which is a local shift, the local climate change driven shifts in weather components. And that allows us to basically project fractional changes induced by this delta on our output. And so that is why the econometric calibration is very important. We are serious people. We try to do it the right way, and we try to replicate the best guys in the world because it is crucial. We are not making up a relationship between temperature and GDP. We are trying to replicate the most famous studies to be sure that we have a consistent understanding of that relationship using real empirical data. And then we can run our projections. You can see that this exercise is a form of supply chain, data processing, econometric calibration, elaboration of the projection data sets, projection, decomposition, distribution. So there is an entire supply chain to run to make sure that we're doing things right, okay? And sometimes we face obstacles, say that there is some data that is not matching, say that there is some missing data in some area. And so the key, when we don't know the answer, is knowing where to look. And so we try to find a way to account for uncertainty because it helps us to provide answers, not saying that these are the best answers ever, but given the data and methodological constraints the world has today, this is probably the least bad solution. And also, we accept anyone to challenge us on that and do better with the data we have. Of course, if you tell me today you have facility level economic information, time series data on a wide numbers of industries and facilities around the world with many information about the structure of their business, I take it. But the question is, if you don't have it, how do you answer the request? And so this is what we could deploy if we were asked to do that. Okay? Well, thank you very much for your attention. It was a long presentation, but I hope, it was interesting. And you can reach out to us at the Climate Institute. We are available to chat. And yeah, feel free to contact us. Okay?